Greetings, physicists. This lecture will be about the forces experienced when you stretch or compress primarily springs, although we will look at some objects that react similarly. So we will start with, we'll take some spring and we will attach it to a surface, in this case the wall on the left side, and we're going to basically let it be neutral. In other words, it's unstretched at the moment. And then we will put a ruler next to it. And just mark off a bunch of distances. And we could measure, for instance, the length of the unstretched spring. And then we could pull that spring, so I'm just going to try and draw a spring that's been stretched a little bit, and we could stretch it further. And what we could do then is, when we stretch it, we can apply, put a little spring or a scale here, like that measures how much force we use to pull the spring. And when we get to a certain distance, like here, we mark the reading on the force scale. And we could do this for a very large range, and then we could, of course, plot it, because that's what we do in physics. Make a plot. And we could say at the unstretched length, so this would be position in like meters or centimeters, and this could be the force reading on the scale in newtons. And what we would find, or what many times we will find, is a relationship that looks something like this. Which is to say a linear relationship. We typically find a linear relationship between force and displacement of a spring. And the intercept value is often, in this case, this value here, the unstretched spring. So usually, another way to do this graph is to say, instead of measuring x, we measure, instead of using this point to be the reference point and saying that we start at some distance x, we would say that this point could be the reference point, and that's 0, and then we move everything this far and see how far we stretch from that 0 point. And if you do that, your graph will come out this way. You'll get a graph that goes through the origin of force versus displacement, making sure that you know that this displacement x is measured from the end of the spring, not the end of the spring connected to the spring scale, this end up here. This end here, not this end here. Okay, so that's set out there. Well, what does this mean when we analyze the graph? Well, a lot of times what we do is we look for the slope of that, right? What if we measured 3 different springs and one of them was here, one of them was here, right? Well, let's think about that. That means let's call them spring A, spring B, and spring C. Well, spring A had the weakest slope, meaning that for some change in x, it had this much change in f. Spring B, for the same length of stretch, x, oh my god, stop there, had this much. So this was A right here. Well, this was B right here. So, had this much force. So it took more force to pull B to this length than it took to pull A. And of course C was so big, the slope was so high that we can barely put it on the same graph. So a spring that takes more force to pull it, we just typically call that the stiffness of the spring. So the K value here sort of represents for each spring how stiff was that spring. C, because it had a steeper slope, must have had a very tough time pulling out a very stiff spring value, where A was a much looser spring. So if we take that slope, that k, what is k equal to? Well, k is delta y over delta x, which in this case is going to be the force divided by the displacement. And oftentimes you will see the equation written out this way, that the force applied to the spring will be equal to this k value, the slope, times its displacement. And we will actually use the letter k in this equation. We call this Hooke's law because the dude who did all the experiments was named Hooke. But that is Hooke's law right there. Sometimes you'll see people put a negative in front of it. We'll talk about that in a little bit. K, back to K. That K we will call the spring constant, or sometimes the elastic constant. And for all intents and purposes, it's just how stiff is that spring. Now, the negative. Why did I put a negative in there? Well, it has to do with this. If we had the spring here, then, and we're stretching it in this direction, so the delta x is to the right, the spring will actually apply a force this way. So the force the spring applies, the spring force, would be to the left. So we put a little s there, the spring force. So all the negative implies, this negative here, is that this displacement and this force are in opposite directions. That's all it means. And I find that students tend to have difficulty when they place that negative into their equations. So when I'm solving these equations, and I do too, so when I solve these equations, I usually don't include the negative in the math, just because it's very easy to misinterpret. But that's true of springs, and so let's take our spring. Let's take the unstretched spring. I'm actually going to draw it in a couple of ways, but I'll start in the middle. Here's our unstretched spring. This is it hanging neutral, essentially, or lying neutral. If I stretch the spring to a distance greater than its what we'll call the equilibrium position. So the equilibrium position is here in the middle. Oh gosh, can I draw? Equilibrium position. If I stretch it to here, to a greater than equilibrium, the force will go back. It'll try to pull the spring back to the equilibrium position. But springs, you should probably know, you can also compress them. You can make them, squeezed. If we squeeze the spring and the delta x is in the opposite direction, then the force will apply forward. So this is like, here's my delta x. My delta x was in this direction for the stretching the spring. My spring force is backward. Here, the delta x went this way. We had a delta x from equilibrium to the left, so the spring will point back. So the force from a spring always points in the direction of the equilibrium position, which is opposite of its displacement. Keep that in mind. This applies to things that are not technically springs. And one example is a rubber band. If you ever stretch a rubber band, like from, let's say this is equilibrium, and you stretch it to a greater distance than equilibrium, the force pushes back towards equilibrium. That can be modeled as a spring force, and it would apply the same Hooke's law, F equal kx, or negative kx. And in this case, the k value is sort of the stiffness of the rubber band, or the looseness of the rubber band. And different rubber bands can have different elasticity constants. So this is still fine. Now, the difference between the rubber band and the spring is you can't really compress a rubber band. It just sort of becomes loose and doesn't squeeze back. The opposite of this would be something like a tennis ball. If you took a tennis ball and you threw it through the air with some velocity at a wall, you would probably notice that when it hits the wall, it compresses, it squeezes into sort of a oblong shape. There's my squeezed tennis ball. Well, if this tennis ball here, this is like the equilibrium width of the tennis ball, and it's squeezed into a shorter width here. So it was squeezed from, I guess the squeeze is in this direction. Well, the force is back in this direction. So that's the delta x. And that's the force. And they're made of rubber, an elastic material. And so we could say the spring force would be equal to the kx of the tennis ball, x being how far it was compressed. But this is kind of the opposite of a rubber band. We don't generally think of you can pull a tennis ball and stretch it. You might be able to for a tiny bit, but you could also risk tearing it in half or something. But they do squeeze very well. That's part of what makes tennis work. So those are like non-spring examples that still follow Hooke's law. There are also, I should say, springs that don't follow Hooke's law. Hooke's law is a linear relationship. It follows y equals kx, which is a straight line equation, right? When we graphed Hooke's law, we got a straight line. There are springs that don't have straight line graphs. Okay, we call them nonlinear springs, and this is typically true of springs that stretch. Like if you pull a spring too hard, you bend it out of shape. If you ever have old slinkies that are like all kinked up and bent into a non-spring looking shape, those are not linear anymore. Those are not going to have nice straight line graphs. So Hooke's law is generally a linear situation for very short distances for most springs. So a lot of times when you're using a spring in an experiment, you want to be very careful not to pull it too far, because then that F equal kx relationship is invalid and you risk destroying the spring. But as far as we're concerned in our class, we will not really be dealing with nonlinear springs, but just to let you know that they exist. Okay, this is the lecture on Hooke's law. Hope it was useful.